Hello students, I'm Rashmi Vadva, Assistant Professor of Sant and Institute of Technology and Management, Gurgaon from ETCE department. I'm the student. Today's topic is from Unit 4, Design of IIR Filter. अब तक के पहले वीडियोस में मैं 2 यूनिट कवर कर चुकी हूँ. ये आपकी नेक्स्ट यूनिट है, दैट इज़ यूनिट नंबर 4. So first of all, what do you mean by IIR filter and a FIR filter? Basically, there are the two types of filters, FIR filter and IIR filter. FIR filter is an finite impulse response and IIR filter is an infinite impulse response. Basically, students, in the designing of IR filter, why we are using all this, our main motive is to design analog filter and then convert it into the digital filter. This is our principle कि एनालॉग फिल्टर को डिजिटल फिल्टर में चेंज करना है. So there are the conversion methods. So there are the 3 conversion methods, and what is our requirement we will discuss one by one. So first of all, difference between FIR filter and IIR filter is what? FIR is an impulse response having a finite length, and IIR is an impulse response having an infinite length. FIR, for the casual FIR system, the equation of the convolution is Fyn summation x0 to m hk xn minus k. For casual IIR system, the equation of the convolution is this one. For FIR system need finite memory. For the FIR system, IIR system requires infinite memory. FIR system, these system can be designed using convolution equation, and the IIR system can be designed using difference equation. It is a non-recursive system and it is recursive system. This is the difference between FIR filter and IIR filter. Now come to the design of IIR filter. So there are the 3 methods, that is approximation of derivative, impulse invariant method and bilinear transformation method. So actually for conversion of analog to digital filter, convert conversion methods are convert differential equation into difference equation, convert continuous time impulse response into discrete time impulse response, and convert transfer function Hs into the transfer function Hz. They are the 3 conversion method. And what is our requirement? Requirement is the left half plane of the S should map into the inside the of unit circle in the Z plane, so that the stable analog filter is converted into stable digital filter. So ये जो 3 methods हैं, approximation of derivative, impulse invariant method, bilinear transformation, ये 3 methods बहुत important है, but जो थर्ड वन है that is bilinear transformation, ये बहुत important है. ये पेपर में 10 मार्क्स में आता है, मोस्टली यही पूछा जाता है, bilinear transformation. So जो फर्स्ट एंड सेकेंड मेथड्स हैं are appropriate for the design of low pass filter and band pass filter whose resonant frequencies are low. These techniques are not suitable for high pass and band reject filter. So the limitation is overcome in the mapping technique, that is bilinear transformation. तो मतलब ये है कि जो ऊपर के 2 मेथड हैं, that is approximation of derivative and impulse invariant method, ये जो है ये यूज होते हैं हमारे लो पास फिल्टर एंड बैंड पास फिल्टर के लिए, और जो थर्ड वन है बाइलिनियर ट्रांसफॉर्मेशन का, वो यूज होता है हमारा बैंड रिजेक्ट और हाई पास फिल्टर्स के लिए. फाइन. सो विल डू वन बाय वन, हमें तीनों करने हैं. सो फर्स्ट ऑफ ऑल इज अप्रोक्सीमेशन ऑफ डेरिवेटिव. सी IIR filter design technique depend upon the converting analog filter into digital filter, and this is the 3 method. So what is the introduction of this is that the system function HAS is stable if all its poles lie in the left half of the S plane. Hence, the conversion is effective. If the j omega axis in the S plane map into the unit circle in the Z plane, and the left half plane LHP of the S plane map into inside of a unit circle in the Z plane. So the stable analog filter will be converted to the stable digital filter. Now, the simplest method to convert an analog filter to a digital filter is to be converted the differential equation into difference equation. This is also called a backward method. Backward difference method और difference method भी बोलते हैं. इसमें हम क्या करते हैं, जो भी हमारी डिफरेंशियल इक्वेशन होती है उसको हम डिफरेंस इक्वेशन में चेंज करते हैं. फॉर द फर्स्ट डेरिवेटिव dy बाई डी टी इज इक्वल्स टू वाई एन टी माइनस टी अपॉन में टी. दिस इज आवर backward this is our related to the difference equation or it is the first derivative equation. And when t common ले लिया तो y n माइनस वाई एन माइनस वन, टी हमारा वन हो गया. ठीक है. सो वाई टी का जब हम ट्रांसफर फंक्शन लेते हैं तो एच एस इज इक्वल्स टू एस हो जाएगा एंड इट्स डेरिवेशन इज डी वाई बाई डी टी. एंड व्हेन वाई एन इज एन इनपुट देन एच एस का हमने उसको चेंज करना है एच जेड में. सो एस की जगह आ जाएगा वन माइनस जेड इनवर्स बाई टी, दैट इज वाई एन माइनस वन अपॉन में टी. For the analog derivative, the system function is given by is like that. Hs is equals to hs, whereas the digital system function hz is equals to 1 minus z inverse by t, which leads to s is equals to 1 minus z inverse by 3. The second derivative is replaced by the second difference equation d square by dt square, differentiation of yt with respect to dt, that is y nt minus t upon t minus y nt minus t minus y n minus twice of t. अगर ऐसे ही बढ़ते चलेंगे तो 2t की जगह 3t आ जाएगा by t upon में t. Then yn minus 2 yn minus 1 plus में y n minus 2 by t square. t ये वाला डिनोमिनेटर में आ जाएगा तो t square बन जाएगा. In frequency domain this is equivalent to h square. Yes, 1 इसको लिखेंगे 1, इसको लिखेंगे minus 2 as it is. This is my z inverse and this is my z minus 2 upon में t square, and so it is a 1 minus z inverse का whole square. तो ये बन जाएगा 1 minus z inverse का whole square और 1 minus z inverse by t का whole square. Then the kth derivative is equivalence to frequency domain relationship is sk is equals to 1 minus z inverse by t की power k. The system function for the Iir filter obtained as a result of approximation of derivative is equals to hz is equals to has and s is equals to 1 minus z inverse by t. Let us investigate the implications of the mapping from the S plane to the Z plane. Z is equals to 1 upon me 1 minus st. Then the j omega axis is mapped into Z is equals to 1 minus j omega t. 1, and when you rationalize this one, so 1 minus omega square by into t square 1 plus में j into आपने जब rationalize किया तो separate real part and imaginary part. The y-axis in the S-plane is mapped into the circle of a radius half and the center z is equals to 1 by 2. Any point in the left half plane will be mapped to the point inside that circle, so the resultant filter is stable. Now, the possible locations of the poles of the digital filter are confined to small frequencies. As consequences, the mapping is restricted to low pass and a band pass filter with a relatively small resonant frequency. It is not possible to transform a high pass analog filter into correspondingly high pass digital filter. It attempt to overcome the limitation. More complex substitution for the derivative has been proposed. सो आपको बस इतना ही करना है, ये इसके कंक्लूजन वाले पॉइंट है। सो यहाँ तक ही अप्रोक्सीमेशन ऑफ डेरिवेटिव है। नेक्स्ट इज bilinear transformation. Let us the system function of the analog filter is Hs is equals to b upon my s plus a. The differential equation describing the analog filter can be Hs is equals to ys upon my xs is equals to b upon my s plus a. So the cross multiply of this ys into my s plus a is equals to b into my xs. Taking inverse Laplace transform dy by dt प्लस a इंटू डी वाई टी वाई एस का ट्रांसफॉर्म हो जाएगा वाई टी, एक्स टी का हो जाएगा एक्स एस का हो जाएगा एक्स टी. द इक्वेशन 2 इज इंटीग्रेटेड बिटवीन द लिमिट्स एन टी माइनस टी एंड टी. So when we are integrating the limits nt minus t dy by dt into my dt plus a yt dt nt minus t integration nt is equals to b xt dt nt minus t nt. So the trapezoidal rule for the numeric integration is given by this. ये हमारे पास एक मैथमेटिकल न्यूमेरिकल मैथ्स में ये ट्रापेजोइडल रूल होता है फॉर न्यूमेरिक इंटीग्रेशन के लिए. So the integration of at dt is nt minus t up to nt, then the equals to t by 2 a nt plus a nt minus t. Apply this formula for the equation number 3, and this is my equation number 3. When we are applying this formula on the equation number 3, then ynt minus t plus at upon में 2 ynt plus में at by 2 ynt minus t is equals to bt by 2 xnt plus bt by 2 xn minus nt minus 10 minus t. So xnt का है xz, इसका इनवर्स हो जाएगा z इनवर्स xz, इसका है yz, इसका हो जाएगा yz z इनवर्स, इसका xz, इसका xz z इनवर्स. So taking the z transform, the system function of the digital filter is when we are doing the z transform of all the system, all the whole the equation, then yz कॉमन ले लेंगे and इधर से xz कॉमन ले लेंगे, then divide by yz by xz is equals to b upon में 2t into में 1 minus z inverse upon में 1 plus z inverse plus a. So this is when we are comparing to this equation number 1, which is equals to b upon में s plus a. So we will get the value of s is equals to 2 by t 1 minus z inverse upon में 1 plus z inverse. The general characteristics of the mapping z is equals to e raised to power st can be obtained by substituting s is equals to sigma plus j omega and expressing the complex variable z in the polar form. Z is equals to r e j omega. When we are putting r g omega, r e raised to power j omega, then when we get the s is equals to 2 by t z minus 1 upon में z plus 1, then it is equals to 2 by t r e j omega minus 1 upon में r e j omega plus 1. So when you separate real part or an imaginary part, then and then take its LCM, then you will get 2 by t and r square minus 1 upon में 1 plus r square plus 2r cos omega plus j into 2r sin omega upon में 1 plus r square plus 2r cos omega. Therefore, when we are comparing this equation with then we will get sigma is equals to 2 by t into में r square minus 1 upon में 1 plus r square plus 2r cos omega or omega is equals to 2 by t into में 2r sin omega upon में 1 plus r square plus 2r cos omega. For unity magnitude, r is equals to 1 and sigma is equals to 0. When putting r is equals to 1 and sigma is equals to 0, then you will get omega is equals to 2 by t sin omega upon में 1 plus cos omega, and 2 by t sin omega into cos omega by 2, and then 1 is equals to cos square omega by 2 plus sin square omega by 2 plus cos square omega by 2 minus sin square omega by 2, and you omega is equals to 2 by t tangent inverse omega by 2, and you will get omega is equals to 2 tangent inverse the angle t by 2. So बेसिकली इसको हम कई बार थीटा भी बोल देते हैं, और थीटा ना बोल के ओमेगा बोल दो, एंड इसको डब्ल्यू बोल दो, साइन डब्ल्यू प्लस में 1 प्लस में कॉस डब्ल्यू. And then this relationship between the frequency in the two domain, it can be noted that the entire range in omega is mapped only once into the range. Then omega is in between minus pi to pi. The mapping is non-linear and the lower frequency is in analog domain are expanded in the digital domain, where the higher frequency are compressed, and this is due to the non-linearity of the arc tangent function and usually called frequency wrapping. इसको हम frequency wrapping बोलते हैं. So when we do problems on this bilinear transformation, क्योंकि पेपर में कई बार bilinear transformation पे एक numerical आ जाता है, so see the question. Convert the analog filter with system function. Hs is equals to s plus 0.1 upon में s plus में 0.1 square 0.1 whole square plus 9, and then into a digital filter convert करना है using bilinear transformation. So the digital filter should have a resonant frequency of omega r is equals to pi by 4. For the system function, we noted that from this we get this frequency, cutoff frequency जो omega c है, that is equals to 3. That is equals to 3 because यहाँ 9 का square है, so you will get this is, yes. And then the sampling period t can be determined. Omega c is equals to 2 by t tangent inverse omega r by 2. That is not omega c, that is you can say that frequency, basically it is cut off frequency. Sampling period is obtained from the above equation. T is equals to 2 by omega c tangent omega r by 2. Omega r is equals to pi by 4, and 2 by 3 is equals to 3 by 3 into tangent pi by 8, that is 0.276 second. Using bilinear transformation, Hz is equals to Hs, and that is equals to S to T by T. So when you are putting 2 by t z minus 1 z plus 1 plus 2, आपने s की जगह 2 by t z minus 1 upon z plus 1 put कर दिया, and so when taking LCM, and you will get this equation, and substituting t is equals to, given है t is equals to इतने seconds, और आपने यहाँ पे t की value 0.276 सेकेंड रख दी है, और देन आपने कैलकुलेट कर लिया, तो आपको ये इक्वेशन मिलेगी. And now apply the bilinear transformation to this question. Hs is equals to 2 upon s plus 1 s plus 2, but the time is 0.1 second. Do yourself. So in this video I am covering two topics, that is approximation of derivative and bilinear transformation. Thank you, students.